Nitrogen, symbol N, is the chemical element of atomic number 7. At room temperature, it is a gas of diatomic molecules and is colorless and odorless. Nitrogen is a common element in the universe, estimated at about 7th in total abundance in our galaxy and the solar system. On Earth, the element is primarily found as the gas molecule. It forms about 78% of Earth's atmosphere. The element nitrogen was discovered as a separable component of air, by Scottish physician Daniel Rutherford, in 1772. Many industrially important compounds, such as ammonia, nitric acid, organic nitrates, and cyanides, contain nitrogen. The extremely strong bond in elemental nitrogen dominates nitrogen chemistry, causing difficulty for both organisms and industry in converting the N2 into useful compounds, but at the same time causing release of large amounts of often useful energy when the compounds burn, explode, or decay back into nitrogen gas. Synthetically produced ammonia and nitrates are key industrial fertilizers, and fertilizer nitrates are key pollutants in causing the eutrophication of water systems. Outside their major uses as fertilizers and energy stores, nitrogen compounds are versatile organics. Nitrogen is part of materials as diverse as Kevlar fabric and cyanoacrylate superglue. Nitrogen is a constituent of molecules in every major pharmacological drug class, including the antibiotics. Many drugs are mimics or prodrugs of natural nitrogen-containing signal molecules. For example, the organic nitrates nitroglycerin and nitroprusside control blood pressure by being metabolized to natural nitric oxide. Plant alkaloids contain nitrogen by definition, and thus many notable nitrogen-containing drugs, such as caffeine and morphine, are either alkaloids or synthetic mimics that act upon receptors of animal neurotransmitters. Nitrogen occurs in all organisms, primarily in amino acids and also in the nucleic acids. The human body contains about 3% by mass of nitrogen, the fourth most abundant element in the body after oxygen, carbon, and hydrogen. The nitrogen cycle describes movement of the element from the air, into the biosphere and organic compounds, then back into the atmosphere. History and etymology. Nitrogen is formally considered to have been discovered by Scottish physician Daniel Rutherford in 1772, who called it noxious air or fixed air. The fact that there was a component of air that does not support combustion was clear to Rutherford. Nitrogen was also studied at about the same time by Carl Wilhelm Scheele, Henry Cavendish, and Joseph Priestley, who referred to it as burnt air or phlogisticated air. Nitrogen gas was inert enough that Antoine Lavoisier referred to it as mephitic air, or azote, from the Greek word a paragraph isotopes, lifeless. In it, animals died and flames were extinguished. This mephitic air consisted mostly of N2, but might also have included more than 1% argon. Lavoisier's name for nitrogen is used in many languages and still remains in English in the common names of many compounds, such as hydrazine and compounds of the acid ion. The English word nitrogen entered the language from the French nitrogen, coined in 1790 by French chemist Jean-Antoine Chaptal, from the Greek I1/2 I1/2 nitron, sodium carbonate, and the French garni, producing from Greek I3 micron I1/2 I registered trademark I genes, producer, begetter. The gas had been found in nitric acid. Chaptal's meaning was that nitrogen gas is the essential part of nitric acid, in turn formed from saltpeter, then known as nitre. This word in the more ancient world originally described sodium salts that did not contain nitrate, and is a cognate of natron. Nitrogen compounds were well known by the Middle Ages. Alchemists knew nitric acid as aqua fortis. The mixture of nitric and hydrochloric acids was known as aqua regia, celebrated for its ability to dissolve gold. The earliest military, industrial, and agricultural applications of nitrogen compounds use saltpeter, most notably in gunpowder, and later as fertilizer. In 1910, Lord Rayleigh discovered that an electrical discharge in nitrogen gas produced active nitrogen, an allotrope considered to be monoatomic. The whirling cloud of brilliant yellow light produced by his apparatus reacted with quicksilver to produce explosive mercury nitride. For a long time sources of nitrogen compounds were limited. Natural sources originated either from biology or deposits of nitrates produced by atmospheric reactions. Nitrogen fixation by industrial processes like the Franca-Euro-Caro process and Haber-Euro-Bosch process eased this shortage of nitrogen compounds, to the extent that half of global food production now relies on synthetic nitrogen fertilizers. At the same time, use of the Ostwald process to produce nitrates from industrial nitrogen fixation allowed the large-scale industrial production of nitrates which fueled explosives in the world wars of the 20th century. Production. Nitrogen gas is an industrial gas produced by the fractional distillation of liquid air, or by mechanical means using gaseous air. Commercial nitrogen is often a byproduct of air processing for industrial concentration of oxygen for steelmaking and other purposes. When supplied compressed in cylinders it is often called OFN. In a chemical laboratory it is prepared by treating an aqueous solution of ammonium chloride with sodium nitrite. NH4Cl, Ac, plus NaNO2, Ac, An2, G, plus NaCl, Ac, plus 2Hours 2O, small amounts of impurities NO and HNO3 are also formed in this reaction. The impurities can be removed by passing the gas through aqueous sulfuric acid containing potassium dichromate. Very pure nitrogen can be prepared by the thermal decomposition of barium azide or sodium azide. 2Nan3 or 2Na plus 3N2. Properties: nitrogen is a known metal, with an electronegativity of 3.04. It has 5 electrons in its outer shell and is, therefore, trivalent in most compounds. The triple bond in molecular nitrogen, N2, is one of the strongest. The resulting difficulty of converting N2 into other compounds, and the ease of converting nitrogen compounds into elemental N2, have dominated the role of nitrogen in both nature and human economic activities. At atmospheric pressure, molecular nitrogen condenses at 77 K and freezes at 63 K into the beta-hexagonal close-packed crystal allotropic form. Below 35.4 K nitrogen assumes the cubic crystal allotropic form. Liquid nitrogen, a fluid resembling water in appearance, but with 80.8% of the density, is a common cryogen. Unstable allotropes of nitrogen consisting of more than 2 nitrogen atoms have been produced in the laboratory, like N3 and N4. Under extremely high pressures and high temperatures, as produced using a diamond anvil cell, nitrogen polymerizes into the single-bonded cubic gauche crystal structure. This structure is similar to that of diamond, and both have extremely strong covalent bonds. N4 is nicknamed nitrogen diamond. Other allotropes include hexazyme, N6, a benzene analog, and octooxycubene, N8, a cubene analog. The former is predicted to be highly unstable, while the latter is predicted to be kinetically stable, for reasons of orbital symmetry. Isotopes. There are 2 stable isotopes of nitrogen, 14N and 15N. By far the most common is 14N, which is produced in the CNO cycle in stars. Of the 10 isotopes produced synthetically, 13N has a half-life of 10 minutes and the remaining isotopes have half-lives on the order of seconds or less. Biologically mediated reactions strongly control nitrogen dynamics in the soil. These reactions typically result in 15N enrichment of the substrate and depletion of the product. A small part of the molecular nitrogen in Earth's atmosphere is the isotopologue 14N15N, and almost all the rest is 14N2. The radioisotope 16N is the dominant radionuclide in the coolant of pressurized water reactors or boiling water reactors during normal operation. It is produced from 16O via reaction. It has a short half-life of about 7.1 s, but during its decay back to 16O produces high-energy gamma radiation. Because of this, the access to the primary coolant piping in a pressurized water reactor must be restricted during reactor power operation. 16N is one of the main means used to immediately detect even small leaks from the primary coolant to the secondary steam cycle. In similar fashion, access to any of the steam cycle components in a boiling water reactor nuclear power plant must be restricted during operation. Condensate from the condenser is typically retained for 10 minutes to allow for decay of the 16N. This eliminates the need to shield and restrict access to any of the feed water piping or pumps. Electromagnetic spectrum. Molecular nitrogen is largely transparent infrared and visible radiation because it is a homonuclear molecule and, thus, has no dipole moment to couple to electromagnetic radiation at these wavelengths. Significant absorption occurs at extreme ultraviolet wavelengths, beginning around 100 nanometers. This is associated with electronic transitions in the molecule to states in which charge is not distributed evenly between nitrogen atoms. Nitrogen absorption leads to significant absorption of ultraviolet radiation in the Earth's upper atmosphere and the atmospheres of other planetary bodies. For similar reasons, pure molecular nitrogen lasers typically emit light in the ultraviolet range. Nitrogen also makes a contribution to visible air glow from the Earth's upper atmosphere, through electron impact excitation followed by emission. This visible blue air glow typically results not from molecular nitrogen but rather from free nitrogen atoms combining with oxygen to form nitric oxide. Nitrogen gas also exhibits scintillation reactions. In general, nitrogen is unreactive at standard temperature and pressure. N2 reacts spontaneously with few reagents, being resilient to acids and bases as well as oxidants and most reductants. When nitrogen reacts spontaneously with a reagent, the net transformation is often called nitrogen fixation. Nitrogen reacts with elemental lithium. Lithium burns in an atmosphere of N2 to give lithium nitride, 6 Li plus N2 or 2 Li 3N. Magnesium also burns in nitrogen, forming magnesium nitride. 3 mg plus N2 or Mg3N2. N2 forms a variety of adducts with transition metals. The first example of a dinitrogen complex is Ru, NH3, 5, N2, 2+. However, it is interesting to note that the N2 ligand was obtained by the decomposition of hydrazine, and not coordination of free dinitrogen. Such compounds are now numerous. Other examples include IOCl, N2, PPH3, 2, W, N2, 2, penthouse 2PCH2CH2 PPH2, 2, and I5C5Me4H, 2ZR2, I1/2, I2, I2N2. These complexes illustrate how N2 might bind to the metal, S, in nitrogenase and the catalyst for the Haber process. A catalytic process to reduce N2 to ammonia with the use of a molybdenum complex in the presence of a proton source was published in 2005. The beginning point for industrial production of nitrogen compounds is the Haber process, in which nitrogen is fixed by reacting N2 and H2 over an iron, II3, oxide, Fe3O4, catalyst at about 500 AA degrees Celsius and 200 atmospheres pressure. Biological nitrogen fixation in free-living cyanobacteria and in the root nodules of plants also produces ammonia from molecular nitrogen. The reaction, which is the source of the bulk of nitrogen in the biosphere, is catalyzed by the nitrogenase enzyme complex that contains Fe and Mo atoms, using energy derived from hydrolysis of adenosine triphosphate into adenosine diphosphate and inorganic phosphate. Occurrence. Nitrogen gas is the largest constituent of the Earth's atmosphere. However, this high concentration does not reflect nitrogen's overall low abundance in the makeup of the Earth, from which most of the element escaped by solar evaporation, early in the planet's formation. Nitrogen is a common element in the universe, and is estimated to be approximately the seventh most abundant chemical element by mass in the universe, our galaxy and the solar system. In these places it was originally created by fusion processes from carbon and hydrogen in supernovas. Molecular nitrogen and nitrogen compounds have been detected in interstellar space by astronomers using the Far Ultraviolet Spectroscopic Explorer. Due to the volatility of elemental nitrogen and also its common compounds with hydrogen and oxygen, nitrogen and its compounds were driven out of the planetesimals in the early solar system by the heat of the Sun, and in the form of gases, were lost to the rocky planets of the inner solar system. Nitrogen is therefore a relatively rare element on these inner planets, including Earth, as a whole. In this, Nitrogen resembles neon, which has a similar high abundance in the universe, but is also rare in the inner solar system. Nitrogen is estimated at 30th of the elements in crustal abundance. There exist some relatively uncommon nitrogen minerals, such as saltpeter, Chile saltpeter and sal ammoniac. Even these are known mainly as concentrated from evaporative ocean beds, due to their ready solubility of most naturally occurring nitrogen compounds in water. A similar pattern occurs with the water solubility of the uncommon light element boron. However, nitrogen and its compounds occur far more commonly as gases in the atmospheres of planets and moons that are large enough to have atmospheres. For example, molecular nitrogen is a major constituent of not only Earth's atmosphere, but also the Saturnian moon Titan's thick atmosphere. Also, due to retention by gravity at colder temperatures, nitrogen and its compounds occur in trace to appreciable amounts in planetary atmospheres of the gas giant planets. Nitrogen is present in all living organisms, in proteins, nucleic acids, and other molecules. It typically makes up around 4% of the dry weight of plant matter, and around 3% of the weight of the human body. It is a large component of animal waste, usually in the form of urea, uric acid, ammonium compounds, and derivatives of these nitrogenous products, which are essential nutrients for all plants that cannot fix atmospheric nitrogen. Compounds. The main neutral hydride of nitrogen is ammonia, NH3, although hydrazine, N2O4, is also commonly used. Ammonia is more basic than water by 6 orders of magnitude. In solution, ammonia forms the ammonium ion, NH+4. Liquid ammonia is amphiprotic and forms ammonium and the less common amide ions, NHA2. Both amides and nitride salts are known, but decompose in water. Singly, doubly, triply and quadruply substituted alkyl compounds of ammonia are called amines. Larger chains, rings and structures of nitrogen hydrides are also known, but are generally unstable. Other classes of nitrogen anions are the poisonous azides, Na3, which are linear and isoelectronic to carbon dioxide, but which bind to important iron-containing enzymes in the body in a manner more resembling cyanide. Another molecule of the same structure is the colorless and relatively inert anesthetic gas nitrous oxide, dinitrogen monoxide, N2O, also known as laughing gas. This is one of a variety of nitrogen oxides that form a family often abbreviated as NOx. Nitric oxide is a natural free radical used in signal transduction in both plants and animals, for example, in vasodilation by causing the smooth muscle of blood vessels to relax. The reddish and poisonous nitrogen dioxide NO2 contains an unpaired electron and is an important component of smog. Nitrogen molecules containing unpaired electrons show a tendency to dimerize, and are, in general, highly reactive. The corresponding acids are nitrous HNO2 and nitric acid HNO3, with the corresponding salts called nitrites and nitrates. The higher oxides dinitrogen trioxide N2O3, dinitrogen tetroxide N2O4 and dinitrogen pentoxide N2O5, are unstable and explosive, a consequence of the chemical stability of N2. Nearly every hypergolic rocket engine uses N2O4 as the oxidizer. Their fuels, various forms of hydrazine, are also nitrogen compounds. These engines are extensively used on spacecraft such as the Space Shuttle and those of the Apollo program because their propellants are liquids at room temperature and ignition occurs on contact without an ignition system, allowing many precisely controlled burns. Some launch vehicles such as the Titan II and Ariane 1 through 4 also use hypergolic fuels, although the trend is away from such engines for cost and safety reasons. N2O4 is an intermediate in the manufacture of nitric acid HNO3, a strong acid and a fairly strong oxidizing agent. Nitrogen is notable for the range of explosively unstable compounds that it can produce. Nitrogen terdide Ni3 is an extremely sensitive contact explosive. Nitrocellulose, produced by nitration of cellulose with nitric acid, is also known as gunkotin. Nitroglycerin, made by nitration of glycerin, is the dangerously unstable explosive ingredient of dynamite. The comparatively stable, but less powerful explosive trinitrotoluene is the standard explosive against which the power of nuclear explosions are measured. Nitrogen can also be found in organic compounds. Common nitrogen functional groups include amines, amides, nitro groups, imines, and enamines. The amount of nitrogen in a chemical substance can be determined by the Kjeldahl method. Applications: nitrogen gas. Nitrogen gas has a variety of applications, including serving as an inert replacement for air where oxidation is undesirable. As a modified atmosphere, pure or mixed with carbon dioxide, to preserve the freshness of packaged or bulk foods. Pure nitrogen as food additive is labeled in the European Union with the E number E941. In incandescent light bulbs as an inexpensive alternative to argon. In photolithography and deep ultraviolet, to avoid a strong oxygen absorption. Dried and pressurized, as a dielectric gas for high-voltage equipment. The manufacturing of stainless steel. Used in some aircraft fuel systems to reduce fire hazard. On top of liquid explosives as a safety measure. Filling automotive and aircraft tires due to its inertness and lack of moisture or oxidative qualities, as opposed to air. Nitrogen is commonly used during sample preparation procedures for chemical analysis. It is used to concentrate and reduce the volume of liquid samples. Directing a pressurized stream of nitrogen gas perpendicular to the surface of the liquid allows the solvent to evaporate while leaving the solute, S, and unevaporated solvent behind. Nitrogen tanks are also replacing carbon dioxide as the main power source for paintball guns. Nitrogen must be kept at higher pressure than CO2, making N2 tanks heavier and more expensive. Nitrogen can be used as a replacement, or in combination with, carbon dioxide to pressurize kegs of some beers, particularly stouts and British ales, due to the smaller bubbles it produces, which makes the dispensed beer smoother and headier. A pressure-sensitive nitrogen capsule known commonly as a widget allows nitrogen-charged beers to be packaged in cans and bottles. Liquid nitrogen. Liquid nitrogen is a cryogenic liquid. At atmospheric pressure, it boils at a 195.8 degrees Celsius. When insulated in proper containers such as Dewar flasks, it can be transported without much evaporative loss. Like dry ice, the main use of liquid nitrogen is as a refrigerant. Among other things, it is used in the cryopreservation of blood, reproductive cells, and other biological samples and materials. It is used in the clinical setting in cryotherapy to remove cysts and warts on the skin. It is used in cold traps for certain laboratory equipment and to cool infrared detectors or X-ray detectors. It has also been used to cool central processing units and other devices in computers that are overclocked, and that produce more heat than during normal operation. Nitrogen compounds. Molecular nitrogen in the atmosphere is relatively non-reactive due to its strong bond, and N2 plays an inert role in the human body, being neither produced nor destroyed. In nature, nitrogen is converted into biologically useful compounds by lightning, and by some living organisms, notably certain bacteria. Molecular nitrogen is released into the atmosphere in the process of decay, in dead plant and animal tissues. The ability to combine, or fix, molecular nitrogen is a key feature of modern industrial chemistry. Previously to the 20th century, access to nitrogen compounds for fertilizers and gunpowder had been through deposits of natural nitrates, such as Chilean saltpeter. However, first the Franca-Euro-Caro process for producing cyanamide, and then the Haber-Euro-Bosch process for producing ammonia from air and natural gas eased this shortage of nitrogen compounds, to the extent that half of global food production now relies on synthetic nitrogen fertilizers. The Ostwald process, developed a few years before the Haber process, allowed large-scale production of nitric acid and nitrate from ammonia, thus freeing large-scale industrial production of nitrate explosives and weapons propellants from the need to mine nitrate salt deposits. The organic and inorganic salts of nitric acid have been important historically as convenient stores of chemical energy for warfare and rocket fuels. Historically, such compounds included important compounds such as potassium nitrate, used in gunpowder, which was often produced by biological means before natural mineral sources were discovered. Later, all such sources were displaced by industrial production, in the early 1900s. Ammonium nitrate has been used as both fertilizer and explosive. Various other nitrated organic compounds, such as nitroglycerin, trinitrotoluene, and nitrocellulose, are used as explosives and propellants for modern firearms. Nitric acid is used as an oxidizing agent in liquid-fueled rockets. Hydrazine and hydrazine derivatives find use as rocket fuels and monopropellants. In most of these compounds, the basic instability and tendency to burn or explode is derived from the fact that nitrogen is present as an oxide, and not as the far more stable nitrogen molecule, which is a product of the compound's thermal decomposition. When nitrates burn or explode, the formation of the powerful triple bond in the N2 produces most of the energy of the reaction. Nitrogen is a constituent of molecules in every major drug class in pharmacology and medicine. Nitrous oxide was discovered early in the 19th century to be a partial anesthetic, though it was not used as a surgical anesthetic until later. Called laughing gas, it was found capable of inducing a state of social disinhibition resembling drunkenness. Other notable nitrogen-containing drugs are drugs derived from plant alkaloids, such as morphine. Drugs that contain nitrogen include all major classes of antibiotics and organic nitrate drugs like nitroglycerin and nitroprusside that regulate blood pressure and heart action by mimicking the action of nitric oxide. Biological role: nitrogen is an essential building block of amino and nucleic acids, essential to life on Earth. Elemental nitrogen in the atmosphere cannot be used directly by either plants or animals, and must be converted to a reduced state to be useful for higher plants and animals. Precipitation often contains substantial quantities of ammonium and nitrate, thought to result from nitrogen fixation by lightning and other atmospheric electric phenomena. This was first proposed by Liebig in 1827 and later confirmed. However, because ammonium is preferentially retained by the forest canopy relative to atmospheric nitrate, most fixed nitrogen reaches the soil surface under trees as nitrate. Soil nitrate is preferentially assimilated by tree roots relative to soil ammonium. Specific bacteria possess nitrogenase enzymes that can fix atmospheric nitrogen into a form that is chemically useful to higher organisms. This process requires a large amount of energy in anoxic conditions. Such bacteria may live freely in soil but normally exist in a symbiotic relationship in the root nodules of leguminous plants and fertilizer trees. Nitrogen-fixing bacteria are also symbiotic with a number of unrelated plant species such as alders spp, lichens, casuarina, myrica, liverworts, and gunra. As part of the symbiotic relationship, the plant converts the fixed ammonium ion to nitrogen oxides and amino acids to form proteins and other molecules. In return for the fixed nitrogen, the plant secretes sugars to the symbiotic bacteria. Legumes maintain an anaerobic environment for their nitrogen-fixing bacteria. Plants are able to assimilate nitrogen directly in the form of nitrates that may be present in soil from natural mineral deposits, artificial fertilizers, animal waste, or organic decay. Nitrates absorbed in this fashion are converted to nitrites by the enzyme nitrate reductase, and then converted to ammonia by another enzyme called nitrite reductase. Nitrogen compounds are basic building blocks in animal biology as well. Animals use nitrogen-containing amino acids from plant sources as starting materials for all nitrogen compound animal biochemistry, including the manufacture of proteins and nucleic acids. Plant-feeding insects are dependent on nitrogen in their diet, such that varying the amount of nitrogen fertilizer applied to a plant can affect the reproduction rate of insects feeding on fertilized plants. Soluble nitrate is an important limiting factor in the growth of certain bacteria in ocean waters. In many places in the world, artificial fertilizers applied to croplands to increase yields result in run-off delivery of soluble nitrogen to oceans at river mouths. This process can result in eutrophication of the water, as nitrogen-driven bacterial growth depletes water oxygen to the point that all higher organisms die. Well-known dead zone areas in the U.S. Gulf Coast and the Black Sea are due to this important polluting process. Many saltwater fish manufacture large amounts of trimethylamine oxide to protect them from the high osmotic effects of their environment. Conversion of this compound to dimethylamine is responsible for the early odor in unfresh saltwater fish. In animals, free radical nitric oxide serves as an important regulatory molecule for circulation. Nitric oxide's rapid reaction with water in animals results in production of its metabolite nitrite. Animal metabolism of nitrogen in proteins, in general, results in excretion of urea, while animal metabolism of nucleic acids results in excretion of urea and uric acid. The characteristic odor of animal flesh decay is caused by the creation of long-chain, nitrogen-containing amines, such as putrescine and cadaverine, which are breakdown products of the amino acids ornithine and lysine, respectively, in decaying proteins. Decay of organisms and their waste products may produce small amounts of nitrate, but most decay eventually returns nitrogen content to the atmosphere, as molecular nitrogen. The circulation of nitrogen from atmosphere, to organic compounds, then back to the atmosphere, is referred to as the nitrogen cycle. Safety: rapid release of nitrogen gas into an enclosed space can displace oxygen, and therefore presents an asphyxiation hazard. This may happen with few warning symptoms, since the human carotid body is a relatively slow and a poor low-oxygen sensing system. An example occurred shortly before the launch of the first Space Shuttle mission in 1981, when two technicians lost consciousness after they walked into a space located in the shuttle's mobile launcher platform that was pressurized with pure nitrogen as a precaution against fire. The technicians would have been able to exit the room if they had experienced early symptoms from nitrogen breathing. When inhaled at high partial pressures, nitrogen begins to act as an anesthetic agent. It can cause nitrogen narcosis, a temporary semi-anesthetized state of mental impairment similar to that caused by nitrous oxide. Nitrogen also dissolves in the bloodstream and body fats. Rapid decompression can lead to a potentially fatal condition called decompression sickness, when nitrogen bubbles form in the bloodstream, nerves, joints, and other sensitive or vital areas. Bubbles from other inert gases cause the same effects, so replacement of nitrogen in breathing gases may prevent nitrogen narcosis, but does not prevent decompression sickness. Direct skin contact with liquid nitrogen will cause severe frostbite. This may happen almost instantly on contact, or after a second or more, depending on the form of liquid nitrogen. Bulk liquid nitrogen causes less rapid freezing than a spray of nitrogen mist. The extra surface area provided by nitrogen-soaked materials is also important, with soaked clothing or cotton causing far more rapid damage than a spill of direct liquid to skin. Full contact between naked skin and large collected droplets or pools of liquid nitrogen may be prevented for a second or two, by a layer of insulating gas from the lead and frost effect. This may give the skin a second of protection from nitrogen bulk liquid. However, liquid nitrogen applied to skin in mists, and on fabrics, bypasses this effect, and causes local frostbite immediately. Oxygen sensors are sometimes used as a safety precaution when working with liquid nitrogen to alert workers of gas spills into a confined space. See also, industrial gas, reactive nitrogen species, yeast assimilable nitrogen, notes. References. Bibliography, Emsley, John. Nature's Building Blocks, An AZ Guide to the Elements. New York, New York, Oxford University Press. ISBN A978-0-19-960563-7. Further reading, Garrett, Reginald H. Grisham, Charles M. Biochemistry. Fort Worth, Saunders College Pub. ISBN A0-03-022318-0. External links, Etymology of Nitrogen, Nitrogen at the Periodic Table of Videos. Nitrogen podcast from the Royal Society of Chemistry's Chemistry World.